Okay. Okay. So, yeah. So, yeah. Sorry, I'm not there in person. Um, let's see if I can actually. The video doesn't seem to be working here, but I went skiing over the holidays and tried to keep up with my son and my grandson, and made a little mistake, and now I'm paying for it. So I just wasn't able to get on the airplane yesterday. And so thanks to the organizers for the flexibility for letting me participate in this way. And I know this is not quite as good as being there because of conversations during the breaks. So if I say anything that's unclear, if you reach out to me by email, I'd be happy to try and answer you. So here we go. Um, Whoops. Okay, it's not. Give me just a sec here. Not sure why it's not letting me advance. Oh, it's okay. There's actually the skiing. Okay, so it seems to be behaving correctly. Now, this is actually not me. I don't ski that well, but this is the person I was trying to keep up with. But it's a beautiful place if you ever have a chance to go there. Uh, okay, so here's my talk. So I'm going to give a talk this morning and tomorrow morning. This talk will just be very general about what are moiré materials and what do their Hamiltonians look like and what do they mean. So this is a topic I've been interested in now for almost 15 years. And over that time, I've worked with many people, and whatever I say to you is mostly things that I've learned from talking to my collaborators over the years. And I'd like to especially highlight Rafi Bistritzer, who was a postdoc in my group 15 years or so ago and is now on the faculty of Tel Aviv University. I started working with moiré materials and graphene multilayers together with Rafi, and also Fengcheng Wu, who was a student in my group and is now a professor at Wuhan University. And Fengcheng and I started to work on moiré material Hamiltonians for transition metal dichalcogenide systems. Okay. So this topic, moiré materials, is one of many ways in which people are, expanding condensed matter physics towards being able to make any kind of, let's say, crystalline system you like by positioning atoms one by one. And it's been clear for a long time that if you could really do that, uh, the range of phenomena that you could see would be tremendous. And so nowadays, when I started doing condensed matter physics, the subject was mainly about understanding and applying the properties of common elemental or simple compound crystals. And now, in many ways, along many different axes, the subject is about really designing materials properties that you can actually realize using different types of ways of growing materials. So, in particular, uh, moiré materials, it turns out, is a great way to make periodic systems, artificial crystals with lattice constants on the 10 nanometer uh, or so scale. I'll say why that scale is important later. Um, and we'd have actually even more flexibility if we could do that by lithography, and maybe eventually we will. But nowadays, moiré materials that I will talk about are the best way of making sufficiently perfect periodic structures on this 10 nanometer length scale that really act like crystals. So moiré material, the word moiré comes from moiré patterns. I'm going to talk about the simplest type of moiré pattern. So this is a bunch of lines, a bunch of blue lines, a bunch of red lines. And if you tilt the, blue lines relative to the red lines, then you can see that the distance between layers varies periodically in the direction, perpendicular to the lines, or a direction along the lines, I should say. And if the smaller you tilt, the longer you period, the longer the period is. So you can see that you can sort of make periodic patterns um, with controllable length scales by making these two patterns slightly different from each other by twisting, and you could do something very similar if the separations between the lines were slightly different. So that's not the type of moiré pattern we're interested in. Uh, this topic is all an outgrowth of the field of two-dimensional materials. The fact that there are methods for extracting individual layers from layered compounds, from van der Waals compounds that have weak interactions between layers uh, and um, and isolating those layers and measuring their properties and as I'll say, stacking them on top of each other. So the materials that have been studied most extensively to date are, layers of graphene, so-called, uh, and graphene is a semi-metal, and group 6 transition metal dichalcogenides, which are in their common structure semiconductors. Um, and in both of these materials, it will be important in what I'm going to say that, graphene is a semi-metal, and that means that all of the low energy states, as indicated by this green circle, are localized in small regions of momentum space. And similarly, in these semiconductors, the low energy states, the states near the Fermi level, for weakly doped systems, uh, are the ones at the top of the valence band, and they are typically near the K point or sometimes near the gamma point in the Brouin zone, but in either case, they're in little small pockets or valleys, as we call them, in momentum space. And as we'll see, that will be important. And so we want to take these two-dimensional materials. We'll be interested, as I'll explain, in cases in which the individual layers are semiconductors or uh, semiconductors or semi-metals. So here is a red two-dimensional crystal. It's actually, square lattice. The lattice points are at the vertices of these intersection points of these lines. And in this case, if you tilt them, you can see again that there's a periodic pattern, and you can characterize that periodic pattern. In this case, I've rotated the blue crystal relative to the red one, and you can see that locally, what you do when you rotate one of the layers is you just change the stacking between the layers. All of the atoms in some little region, if you can see my cursor, in this region, in the white regions here, the red atoms, lattice are right on top of the, right below the blue ones. And as you move through the crystal, you're basically just slowly moving the blue lattice rigidly relative to the reg one. So that's a moiré pattern. And so moiré pattern has a long periodicity. Uh, um, and it's actually not, if you strictly look at all atomic positions, it's not a crystal. The two layers together are not a crystal. But the moiré pattern, the pattern, a very spatial variation of the stacking is periodic. And it's that periodicity that defines the moiré pattern. Uh, what's going on at atomic length scale? One way of thinking about it physically is that if all of the electrons we're interested in are close together in momentum space, then they can't resolve, uh, um, can't resolve structure in space on a length scale smaller than the range of momentum that is relevant. And by a Heisenberg uncertainty principle type argument, and therefore they don't see what's going on at atomic scales. So the effective Hamiltonian depends only on the moiré pattern, and low energy discretes are described by periodic Hamiltonian. So here's another way of saying that in momentum space. So I have two crystals with reciprocal lattice vectors G and G prime. The primitive lattice vectors G sub A and G sub B, are, if the two similars are crystal, the primitive lattice vectors are almost the same. They may differ, for example, if it's just a twist by a rotation. Now, if I consider the effect of the primed layer on the unprimed layer, I can, take all of the Bragg scattering by reciprocal lattice vectors G prime um, that an electron in the unprimed layer would see due to its interaction with the primed layer. If I take all those scattering vectors and reduce them to the Brouin zone of the G layer, you can see that I get a set of points in momentum space specified by 4 integers. So that's not a two-dimensional crystal. It's actually a quasi-crystal, as I was saying. But if I'm only interested in small momentum transfers, then you can see that I have to choose to get, if the reciprocal lattice vectors are similar, there's a set of small momentum transfers I get by choosing these integers n to be the same in the primed and unprimed layers. And so that gives you a set of momentum transfers that are labeled by 2 integers, and these quantities in round brackets here are the reciprocal lattice vectors associated with that crystalline pattern of, Bragg scattering, if you like. And in the case where G prime differs from G by just a rotation, then the set of momentum transfers are proportional to the twist angle. Uh, if I rotate and take the small twist approximation, and uh, and perpendicular to the original reciprocal lattice vectors, which is one way of understanding the patterns I was showing you in momentum space. Okay, so the simplest moiré material is transition metal dichalcogenide, group 6 transition metal dichalcogenide like tungsten diselenide or molybdenum selenide, hetero bilayers, two different materials. So two different materials so that the electrons or holes, the relevant states at the top of the valence band. So in this sketch here, this is energy vertically and position horizontally, tungsten or molybdenum layer. And so the states are basically in the tungsten layer, but they see a weak potential due to the molybdenum layer. And if I look at the energy of the top of the valence band as a function of the stacking between the layers, that tells me that the energy here, varies by something on the order of 100 MeV, or let's say in this calculation, 60 MeV. And this is plotted as a function of stacking in units of how far one layer has locally moved relative to the other. So the period of the moiré pattern is when the stacking vector d, the local displacement of one layer relative to the other, has shifted by a lattice constant. So when I map this stacking d to position for a rigid rotation, then this um, dependence of energy on D turns into a dependence of energy on position at potential that has a length scale. That's the length scale of the moiré pattern. And since the reciprocal lattice vectors of the moiré pattern are proportional to twist angle, the period of the stacking is proportional. The period of the variation is proportional to inverse twist angle. That's the moiré length scale. And so I get an effective potential, which in practical cases, of course, in these hetero-bilayer systems, the lattice constants in the two layers aren't exactly the same. So that's another way in which the reciprocal lattice vectors differ. And it turns out in the end that typically, the moiré periods are on the sort of 10 nanometer scale that I mentioned. So in the end, in this system, you just have an effective potential that's periodic, has a size of 50 MeV or so. I should have pointed, let me skip back here. Whoops. I should have pointed to the fact that the states in the valence band in these materials these materials don't have inversion symmetry, and the states in the valence band are at non-zero momentum. At K in particular, there's no spin degeneracy. There's a large spin splitting. We're only interested in one spin state at each momentum, but they're in a triangular lattice system like this. There are two inequivalent Brouin-Zone corner momenta related by time reversal. And so when you include both of those regions of momentum space, you get two spin states. And so this system is described by periodic Hamiltonian for spinful electrons in a periodic potential. If I look at low energy states, there will be favored energetic positions in each unit cell of the moiré pattern, and the holes will tend to go to those positions. And in order to tunnel from one of those favored positions in one moiré cell to another, the electrons have to go through classically forbidden positions, and that means that the widths of the bands of the effective periodic moiré Hamiltonian can easily be adjusted to very small values by making the moiré period long, so that you have to tunnel for a long distance through classically forbidden region. So in the end, this system is a realization of a Hubbard model. It's basically as close to a real Hubbard model as any physical system. And, like coal atom systems, if you like, it's a Hubbard model simulator. I haven't talked about lattice degrees of freedom, but clearly in these moiré patterns, lattice degrees of freedom remain, and that means that there's no problem cooling the fermionic degrees of freedom. The electrons are holes, and which is a big problem in cold atom systems. So as a Hubbard model simulator, there are lots of advantages of this system. Okay, anybody have any questions? Just shout them out, or let me know if somebody has a question or comment.
Can I be heard? Yeah, just speak loudly. Can you hear me?
Yeah.
Oh, I'm just wondering, I maybe missed it. Where do the interactions come from in the array? So you said it's like a Hubbard model. Yeah, I assume there's like some kind of on-site.
Yeah, so electrons always interact with each other, of course. And, this sort of Hamiltonian um, is it's actually calculated by doing a DFT calculation. So it includes interactions between the electrons and holes, but just like is often true in condensed matter systems where we're only interested in states near the Fermi level, there's always sort of implicit part of what we view as the single particle Hamiltonian. And I'm asking you to view this potential I'm plotting here as a single particle Hamiltonian, comes from interactions with bands that are far away and that I'm not going to explicitly deal with. But more pertinent to your question, once I add holes, more than one hole to this system, then I have to include the interactions between those holes. And that's why, so this is the single electron Hamiltonian is just a periodic potential. Uh, um, and for spinful electrons. That produces bands. Those bands can be narrow, as I tried to say. And once you populate those bands with electrons or holes, you have to include the interactions between the electrons and holes. And in particular, if you want to put more than one hole in the same moiré unit cell, there's a big energy cost for that. And that's the Hubbard U. It turns out that energy scales, typically 50, 100 MeV, let's say. Okay?
Okay.
Okay, anything else? Okay, so shout out, anybody feel free to shout out as I go along. Too bad I can't see you. That's one of the disadvantages of this. So I have to rely on you to shout out. Okay, so I mentioned before that it's nice to have uh, artificial crystals, periodic Hamiltonians, in other words, that have a length scale of 10 nanometer or so. And the we'll talk, they're more complicated Hamiltonians that can and have been realized experimentally than that simple Hubbard model case. But in all of them, the important thing about the length scale is that you can, the number of electrons per moiré period plays the same role in these systems as the number of electrons per atom in a real crystal. And we know in a 2D system by gating, you can change the number of electrons in a 2D system. You cannot change the number of electrons. Typically the maximum change that's possible in a 2D material in terms, by field effect gating is if I want to measure it in terms of electrons per atom of that material, it's much less than one. A typical number might be the most you can change is let's say 10 to the minus 3 electrons per atom. It's kind of obvious that if you actually change the number of electrons by 1 electron per atom, you'd actually be completely changing the chemistry, and and the electrons and all the host atoms would move around. In practice, you usually get to dielectric breakdown of the dielectrics that are part of the gates in these systems by about 10 to the minus 3 electrons per atom. But at a 10 nanometer scale, the number of atoms per period of the moiré pattern is around 10 to the 4. And that means that I can typically change the number of electrons um, per effective atom in these moiré crystals by about 10. And that's, equivalent to be able to moving across large swaths of the periodic table just with gating without any chemical doping whatsoever. And almost every experiment in moiré materials, the x-axis of some plot uh, is uh, is um, is the number of electrons per atom. And that's really one of the things that's so attractive about these artificial crystalline interacting electron systems. Okay. So moiré materials, when I started to work on this, was mostly just an idea, and it's people didn't have any at the time systematic ways of controlling, for example, the twist angle between two adjacent layers. Um, but the subject has become most interesting because experimenters have actually developed the techniques to, in case of many materials, to actually realize different types of moiré Hamiltonians. And that means that we actually can do experiments and find out what the properties of these artificial crystals are. Here, I've paraphrased something I ran across one time, written by Martin Schwarzschild. It was actually written about theories of stellar evolution, but it's something I believe in that without the interplay between theory and experiment, we're unlikely to understand the full richness of different systems. And so now that we're able to do experiments, there are lots of we have this beneficial interplay between theory and experiment that has always been traditionally part of the charm of condensed matter physics. And so now we really have that with moiré materials. And with the various materials, this is a possible table of contents for a course on condensed matter, solid state physics. Uh, you know, um, uh, and pretty much every aspect of condensed matter physics, at least on this list, has been seen in moiré materials experimentally, and uh, and even some that have never been seen before. And one of the most interesting things in moiré materials has been the discovery of the fractional anomalous quantum Hall effect. And I know you're going to hear some other speakers talking about this, but this will also be mostly the subject of my lecture tomorrow. Okay. So now I'm going to say something about, exactly about deriving, I call it here, the moiré band Hamiltonian. This just means sort of understanding what should the single particle part of the Hamiltonian look like. For the interaction part, and interactions, if I populate these bands with carriers, I have to include interactions between those carriers, as one of you brought up just a moment ago. And those interactions are always Coulomb interactions, but there's a lot of variability even within the scope of moiré materials in terms of what the Hamiltonians can look like, depending on the host materials and twist angles and exactly how they're stacked and so on. And so, uh, so I was trying to suggest before that the moiré pattern adds to the Hamiltonian some terms that produce a set of momentum transfers, a set of scattering wave vectors, which actually are can be viewed as, you know, crystal momentum transfers, Bragg scattering, if you like. And so if one way to actually, you know, and yeah, let me step back. So, and in order to, say what the single particle part of the Hamiltonian is, and in other words, what the Hamiltonian is if there's only one electron in those bands, uh, um, I have to calculate, I have to calculate the coefficients, the scattering amplitudes that accompany those scattering wave vectors. And, one way you could do it, for example, is by taking a large supercell. So whenever I have these moiré patterns, and I have these two layers, primed and unprimed, if you like, and they have different reciprocal lattice vectors, but similar. And um, if there's a commensurate relationship between those reciprocal lattice vectors, that means that eventually, even though eventually the set of points that you generate in momentum space, the set of possible momentum transfers, doesn't fully occupy all possible momentum transfers. Instead, you get a crystalline array with a large period. In other words, anytime I have a moiré material uh, for a generic twist angle theta, the real underlying system is not periodic, is not crystalline, but there'll always be a discrete set of twist angles uh, for which there is some long spatial period, a very small reciprocal lattice vector, uh, um, much smaller than the moiré reciprocal lattice vectors, which form a lattice. And so you can just do a direct calculation of the Hamiltonian of such a large supercell, and that will tell you what the terms are in the Hamiltonian at the moiré reciprocal lattice vector wave vectors. And so that sort of method is one way to calculate what these Hamiltonians are. I'm going to talk mainly here about another way, which I call local stacking approximation. It also relies on, treating the system with before the bands are occupied by carriers using DFT. So using, some DFT-like mean field approximation typically. Um, but doesn't involve a large supercell. So this, I think, this local stacking approximation I'll talk about is intended to, partly be a way of theoretically calculating band Hamiltonians for the moiré materials, and partly a way of just sort of visualizing or, conceptualizing what the Hamiltonians should look like. And and it also makes it clear that, there'll be this local stacking approximation will lead to Hamiltonians that are characterized by a relatively small number of parameters. And so, in principle, all of these empty band calculations are approximate, and if you view those parameters that I'll come to in just a moment as um, if you view them as uh, you can view them as phenomenological, and if you are able to determine the values of those parameters from experiment, uh, that's uh, that's better than trying to approximately calculate it. So yeah, so I'm going to talk a little bit about this local stacking approximation, which is certainly the way I think about this. Um, so this kind of approach was first used, I think, by in this paper in PRB in 2014 for a moiré material formed from a layer of graphene on hexagonal boron nitride. And yeah, so boron nitride is the 3,5 version of graphene, has nearly the same lattice constant, but not quite the same. And so if graphene is aligned or nearly aligned to HBN, then there's a moiré pattern. And the starting point for this approach is to first calculate the Hamiltonian as a function of stacking. And so D here is the local stacking. For rigid rotation of one layer relative to another, then the displacement produced by a rotation is just linear in position. Uh, um, um, it's only the position modulo lattice vector that's going to matter, but that's a rigid rotation, and you can take into account strain effects. I'll mention in a minute. But the so uh, the microscopic information that's if you want to think of it this way, that's used to build the model. But I also want, if you think, if in the end we're going to do it phenomenologically, this is a way of thinking about what the parameters we're going to end up with actually mean. Uh, and so here is the local Hamiltonian for two layers with one layer displaced by a stacking vector D, which is just a displacement of one layer relative to the other at some point in momentum space. And that's what we're going to use to build the Hamiltonian. How does the Hamiltonian depend on the rigid, on the stacking between the layers? And the so here, this Hamiltonian is written it's imagined to be written, it's assumed here that this is this is some tight binding representation, some Wannier function Hamiltonian of two or more layers with some stacking of some group of layers relative to the other layers, some displacement. So the labels here on these Hamiltonian matrix elements are L is layer. Okay, so we allow layers to be you can have like layer interactions and opposite layer interactions, L equal L prime, L not equal to L prime. Within each layer, depending on the situation, you might have a number of relevant orbitals. And uh, the um, so in principle, I could, uh, um, write this um, displacement dependent Hamiltonian as in a plane wave representation, so that's often how electronic structure calculations are done in a plane wave representation. And but uh, just the nature of these systems, we want one of the layers to be if more than one layer is involved, it has, a significant role to play in the problem. We want one of the layers to be one of the labels to be layer. And just because it's the physically natural thing for the problem. And so if we want one of the layers labels to be layer, then the way we can do that systematically is to use a Wannier representation and construct an effective Hamiltonian in the representation of Wannier functions that are always localized in a definite layer. So that's why we use Wannier functions. And in some problem, by layer, you have Wannier functions. You have some set of orbitals that are important in a certain range, and you can calculate what the Hamiltonian looks like as a function of displacement between the layers. And uh, hang on just a second. Yeah. Okay, so that's the microscopic information in this approach that you get from doing a DFT calculation. Now there's an observation you can make about how these moiré Hamiltonians depend on D. And the physical basis of this observation that I will make is based on the fact, as I'll emphasize again later, that these moiré Hamiltonians basically only work for strongly layered compounds with strong bonding within layers and weak, effectively, mostly van der Waals interactions between layers. Um, and because of that nature of the chemical bonding in these materials, it's always true that the distance between layers is the lattice constant, if you like, in the layer direction is much bigger than the lattice constant within layers. And so when you look at this dependence of stacking, basically you're looking at the effect of a faraway layer on local properties in one layer. And there's no way that because the other layer is far away, its dependence as you move it, it will the dependence on the of the Hamiltonian on that parameter will be smooth. Um, and because it's smooth, it's natural to Fourier transform it. And the non-constant terms, the dependence on D, this Hamiltonian is basically periodic in D. And so if I Fourier transform it, I only get coefficients at reciprocal lattice vectors. And what I'm really arguing is that typically it's only the first shell of those reciprocal lattice vectors or the smallest momenta transfers that are significant. And that means that and typically, within a shell of momentum, all of the parameters are related to each other by symmetry. So there's only that leaves you with a Hamiltonian that depends only on a small number of parameters. And th those parameters are basically these Fourier transforms with respect to displacement. It's just a way of simply characterizing the dependence of the local Hamiltonian on stacking. And so there's two little asterisks I need to apply here. And um, that is that, if I actually construct this Wannier function, then and representation the way I described for every displacement d, then if I change the dis if I translate, let's say, the top layer of a bilayer by a lattice constant, then just the way I'm labeling the Wannier functions, the system really returns to itself, but the way on which I'm labeling, what I consider to be R equals 0 in one of the layers uh, changes when I change D by a lattice constant. And therefore, in this Wannier representation form, the Hamiltonian matrix elements are not quite periodic and D if the wave vector I'm interested in is non-zero. There's an extra phase factor of e to the I wave vector dot displacement. And so the thing that's periodic is you have to take that phase factor away. So that's a little uh, um, uh, detail that is important in the end. And let me see, I think yeah. And So one other thing I should mention, and that's I'm now putting my cursor around the equation related to the second point I mentioned. I think I actually messed this up when I put these slides together, but I meant to separate this into two slides. But what very often happens is I think I'm missing a slide. Let me just look here. I am. Okay, I'm not. Okay, so ignore this equation. Okay, I'll come back to that in a moment. Uh, um, so so that is, this local stacking approximation gives you a Hamiltonian that is dependent on local stacking. And uh, if I look at the G equals 0 terms in this Fourier expansion of the Hamiltonian, that's the average over all stackings. And so that term, its dependence on the G equals 0 term in the expansion is the dependence on doesn't have a dependence on stacking. It's just the average over all stackings. And so if I look at the Hamiltonian, it produces, it has the symmetry of the host crystals, has the reciprocal lattice vector, and conserves momentum within the Moiré-Bruin zone. And this term really is, basically the host crystal Hamiltonian. As I'll mention later, emphasize later, all of these stacking dependent terms have to be small compared to the bandwidths in the host crystal, or this construction won't work. Um, so this is the Hamiltonian I basically have without the Moiré pattern. And the terms that I have, the position-dependent terms with the Moiré periodicity, are are come from the other terms, and both these interlayer terms, as I was saying before, they can depend, the momentum transfer can be shifted from the moiré reciprocal lattice vectors if we're talking about a non-zero momentum. I'll come back to that if anybody asks any questions. And but uh, so uh, so if I'm interested in states, uh, uh, the um, the second part, the way these parameters appear in the Hamiltonian is similar to the way we often use envelope functions in semiconductors. Basically, the K dependence is retained only in the stacking independent term. Um, and the which is this K dependence is large across the full Brouin zone. The Hamiltonian varies by the bandwidth, if you like, but it's small in the small regions of momentum that are relevant to us. And so the momentum dependence, if I tried to include the non-zero G terms in a momentum dependent way, which is it's normally not done, hasn't really been done yet, but you can do it, sometimes included, but they're small for two reasons and normally negligible. They're small because the moiré modulation is small, and they're small because the region of momentum is small. So we can drop those. And these position dependent terms can be just evaluated at the center, so K star here, at the center of the momentum range of interest. So you end up with effective Hamiltonian, that's the host Hamiltonian, plus a bunch of momentum transfer scattering terms that capture the Moiré physics that are produce momentum shifts, and they're all evaluated at the central momentum, both intralayer and interlayer terms. And so here's the thing I was stumbling over before. There was an equation on the previous slide that should have been deleted. Here it's expanded. And so if you follow this recipe, then when you construct the Wannier functions, as many of you know, you're using states across the full band of the system. And so the number of states the number of bands that you need to include, which are kind of isolated for chemical reasons from other bands, might be bigger than the number of bands that actually are present at the low energies. So a simple example of that is the graphene and HBN case. If I have a tight binding model, the graphene is gapless, HBN is gapped, and so there's a big range of energy of interest where only the graphene orbitals are close to the Fermi energy. So the graphene, the pi orbitals on the graphene are the low energy electrons, and the pi orbitals on the HBN are the high energy electrons. I actually copied this equation from a recent paper by my postdoc, Perry Mahan, and others on M-valley systems that is on the archive recently. Andre Bernevig, whom I think is there or will be there, is and his collaborators have done extensive work also recently on these M-valley systems, and that's an example of a system that is relevant basically to group 2 TMDs. Haven't been studied much experimentally. I haven't seen any data, but I think there is data, and you might hear more about it in the course of this week. But in the case of graphene on HBN, this label M here is shouldn't be present. The states are still centered around K valley. And but in any event, if you physically, it's desirable to have models in the end in which the only orbitals that are retained are the ones that are directly present at low energy. And so you can include the coupling to these high energy orbitals. For example, hybridization between graphene orbitals and boron and nitron orbitals in nearby layers perturbatively by this kind of perturbative expression at the bottom to reduce the model to the number of bands that are present, in the small region of momentum space that you're interested in. So two-band models for graphene on HBN, for example. Okay. I'm nearly at the end. I guess I should be nearly at the end.
But, there is sorry. I have one other question.
Yeah, thank you. Go ahead.
Just so I understand again. You take the Fourier transform of the placement vector D. Does that mean you're actually imagining an infinite layer system? Or
yeah, so D is these calculations are typically done for bilayers.
Right.
Okay, and you could generalize that to many layers, but at least in the most straightforward application, some group of layers will be translated relative to some other group of layers by a displacement layer D, by a displacement vector D. So D is a translation, of, let's say, the top layer relative to the bottom layer in the XY plane.
Oh, in XY.
Yeah. So D is XY plane, and these are all 2D Fourier transforms.
Oh, okay.
And so everything's viewed as a 2D crystal.
Okay.
And this gives me an opportunity to mention that, for each value of D, you can let the layers relax. It very often happens that part of what changes in the Moiré pattern is that the equilibrium distance between layers varies depending on, uh, depending on what the stacking is, because the weak chemical bonds that remain are maybe more or less favorable at one stacking or another. And so the distance between layers will vary. And you can include that, and that is included in the dependence on D. Okay, anything else?
Yeah, I have a.
Yeah.
So you mentioned before that you need so in order to view the potential of the other layer to the present layer to be smooth, we need the displacement vector. We need the distance between the two layers to be large. How large should that be?
I was trying to make a qualitative argument that the dependence of the Hamiltonian on stacking will vary smoothly with stacking. And so the way in which you can test that approximation is you can just calculate, and in this approach, the dependence on stacking and see whether it's smooth. A quantitative way of saying what you mean by smooth is whether in these Fourier expansions, the second shell is much smaller than the first shell or not. Okay. And so, there are various ways I'll mention at the end, in which this Moiré models don't necessarily work for any 2D system, even if there's a moiré pattern. And I'll talk about ways it can, the approximations can fail. I'll mention just at the end. Okay, so here's an example of, go ahead.
Oh, yeah, so for the heteroband layer that you mentioned before about with a low energy band and a high energy band, does that have effect on how large the distance between the two layers needs to be in order to have the function, the potential to be?
In order to have, I didn't get the very end.
Oh, in order to have the potential to have
Be
the
smooth.
If it is a heteroband layer with a low energy band and a high energy band, does that have effect on the distance?
Yeah, whether that perturbative, when that perturbative method of capturing the hybridization with higher energy bands, when it fails, you can just keep those bands in the theory. And that will end up giving you a Hamiltonian with, in which the Hamiltonian acts basically on a spinor space, which is the number of orbitals that you retain. And you can just keep increase the number of orbitals when it fails. But I think in every case, I know, that certainly all the systems people look at so far, this first shell of leading shell approximation for the dependence on stacking is, usually works to a sort of a 1% level.
Thank you so much.
Yeah.
Yeah,
Okay.
we should let Allan finish his presentation because there will be an alarm. For some security alarm at 10 exactly will be loud. We don't have to leave the room, but this will be an interruption. So,
So are you telling me I should stop now? I can finish this part tomorrow.
No, we have to stop it before 10.
Which is 5 minutes, right?
Yes.
Yeah, so why don't I stop here and I'll make this little thing before I go into my main talk tomorrow. This is just sort of saying how the models of twisted bilayer graphene fit into the what I've said so far, and to wrap up thinking in the future about different types of materials, layered materials that people haven't tried yet. What are the conditions for being able to derive effective periodic Hamiltonians that will really describe the system? I have a few comments on that, and I'll start with that next time. So why don't I use the remaining 4 minutes before the alarm sounds to see if there are any other comments or questions anybody wants to make, and I can actually stop share so I can see you.
Very good question. I have a question. So, twisting the two layers is not equivalent to translating one layer with respect to the other. So, why is the stacking vector D that we are defining a constant in the Hamiltonian? Did it have some dependence on real space?
So in principle, this is, the first step of some sort of gradient approximation you could make. The stacking varies on the moiré length scale, okay, which is much bigger than a lattice constant. In principle, you could try to make corrections, and you can you can think about how you would try to calculate the coefficients of these corrections for gradients of D. But the gradients of D are small because the moiré periods are long. And so, it's the first term in a gradient expansion, and we normally don't include the other terms.
Any other question? Here's one.
So the stacking vector D is one. It's a single vector, right? So in this local stacking approximation or the moiré Brillouin zone is 1D. Or
Say that again.
is the moiré Brillouin zone 1D?
No, so D is a two-dimensional vector. So D is the stacking, and if I say it roughly without caveats, D is a parameter that describes the local Hamiltonian at a specific point in the system.
Right,
And
but there's only one vector D, right?
no, D is a 2D vector.
It's a 2D vector, but you could like put it on the x-axis or something like that, right?
What do you mean you can put it on the x-axis?
Well, you said it's in the xy plane, right?
Yeah.
So you could like choose D to be on the x-axis.
No. So D varies as you move through the moiré pattern. I probably should have put in equation in the rigid rotation approximation for a HOMO bilayer. D is just, twist angle times unit vector Z cross R. R is position. So D varies continuously with position, and all values of D are explored. But the Hamiltonian only depends on D modulo host lattice vectors. And that's why, even though D in a moiré pattern varies over an infinite extent, the actual Hamiltonian is periodic. But it's a 2D vector, and it's a 2D vector that is a function of position. Okay, and covers all values of D when you go through all space.
One final
In
question.
a 2D plane, yeah.
Is it at all useful to think of a twist angle as a vortex in D?
A vortex in D. So if I haven't talked very much about including strain relaxation, I'll mention that in the part I didn't get to quite, but the local the curl of D is the local twist angle, and when you include strain relaxation, the local twist angle is not constant, but it varies periodically within the moiré pattern.
Okay.
Yeah.
It's a good time to stop, so let us thank Allan.
Okay, so see you tomorrow.